right? I thought there'd be data. Is anyone out there?
Okay, we are back. And how is problems 1 through 3 with the homework going? The last two we're going to talk about today. The number 1 is just kind of a busy work thing, but we needed to get it out of the way because it is proving the kind of surprising or maybe not surprising result that the sample mean and the sample variance are independent for the normal distribution. It's not for all distributions though. And so people think, myself included, that this is surprising because the sample variance includes the sample mean in its definition. You know, it is a function of the sample mean. But on the other hand, it is not surprising because the sample mean is giving us kind of a location on a number line of our data, and the variance is spread, and they kind of maybe don't depend on each other. And this is true for the normal distribution, and we're going to need this result later, so it's just kind of a big Jacobian problem, and I hope that's going okay. Number 1 takes a little bit of time just organizing things, but otherwise it's going to be pretty fast homework. And we have an exam coming up, and it's next Thursday from 6 to 8, and I'll be sending out a Zoom link for that. And later today, I will be posting review problems, and you will get a table of distributions, and the problems will be easier than homework problems in the sense that they'll be much more straightforward. You know, just, can you do this? Do you know how to do this? What is this? Not, you don't have to be clever. And we can go over those review problems next week. And you'll have next Friday off to give back to you the time you put in on Thursday evening. So the first thing we're going to do is something very strange for us in this class, and that is something kind of numerical. We're going to look at some numbers for a bit. That's because we're just going to try out the central limit theorem. We're going to do just a quick example of the central limit theorem and then move on. We're going to need the central limit theorem throughout the course, so it's not like we're moving past it, but we're going to just do a numerical example. And so to do that, you need to know how to compute probabilities for the normal distribution. So I'm just going to write CLT, which stands for central limit theorem. And people generally use the letter Z to denote a standard normal random variable, which is a normal random variable with mean 0 and variance 1. And it's not that special of a letter, so Z could also mean something else. But if you look at the normal PDF, you can show that it integrates to 1 using polar coordinates, but you can't integrate it up to an x. You can't integrate it over the kind of rectangular region. So in other words, we do not know the CDF for the standard normal or any normal in closed form. So we're going to appeal to a table just briefly and then never again. So I think I've mentioned this already, but a capital phi is usually a special symbol that's used to denote the CDF for a standard normal. And so how do we get a number like, just do a couple of quick examples, the probability that Z is less than or equal to 1.63, well, someone worked these out numerically and tabulated them. And if you go, you don't have to go there, but I am going to share a window so I can show you in the back of the MathStat notes, in an appendix, Appendix C, there is a table, Table C1, that is entitled Standard Normal Probabilities. And how you read this table is, so here you see the phi, it's using the same notation as us, and it's telling you it's the CDF of the standard normal. And we want the probability that Z is less than or equal to 1.63. So you go down this side column here and find the first 2 digits, 1 and 6, or 1.6. And then you go across the top to the 0.03. And in that intersection, you find this probability, which is 0.9484. And if you've never done this before, then you're not doing it now. Just, you know, take a moment sometime to make sure you can find these numbers and match them with the numbers you're finding in your notes. Okay, so back to for us, after today, we're going to get back to our theoretical stuff. And what we're going to use is, given a standard normal distribution, we're going to want to find values that cut off certain areas in here. And we are going, if we want to cut off area alpha here, where alpha is a number between 0 and 1, then we're going to call this cutoff a critical value, and it's going to be denoted by a lowercase z sub alpha. And you don't have to write that down because I'll do it when we get to it. But this is the sort of thing we're going to be looking at, not the actual numbers, but symbols for numbers that cut off certain areas. Okay, so continuing over on the left side with another bullet, the probability that z is less than 1.63. It's a continuous distribution, so there you go. By the way, if you are trying to find the CDF for a number like 1.64, I would not recommend, I mean, it's not bad, but I don't think it's worth interpolating between the numbers on the table. Instead, I think it's fine. Most people just take the closer value on the table. Okay, so as a third bullet, suppose we want the probability that z is greater than 1.63. The probability z is above 1.63 is the complement, so it's 1 minus 0.9484, the rest of the area. And then what I was drawing the picture for was the probability that z is less than or equal to negative 1.63. So by the symmetry of the distribution, this is the same thing as the probability that z is greater than or equal to positive 1.63, which we can then grab from the table. Okay, so this is a table for the standard normal distribution. That means the mean is 0 and the variance is, we don't want to tabulate all the different normal distributions. So we want to use the fact that we can take, for a general normal distribution, we can standardize it and make it into a normal 0, 1. So suppose that we have a random variable x that has a normal distribution with mean 2 and variance 5. And just to remind you, we're using a pretty standard notation where we put in the mean and the variance, but sometimes, and I will never do this, some books, some papers actually parameterize it in terms of the standard deviation. And I didn't cross it out because it's wrong, but I crossed it out because we're not doing that. Okay, so if you take any linear combination of normals, you get another normal. And this includes not just combining like an x1 and an x2, but multiplying and dividing and adding and subtracting constants. So if you take any random variable minus its mean and divide it by its standard deviation, it's really easy to show, just take the expected value and variance, and it's really easy to show that this is going to be 0 and this is going to be 1. And because of that nice linear combination property that we can show with moment generating functions, the random variable that I wrote there, the x minus mu over sigma, is normally distributed with mean 0 and variance 1. So if we want to find a probability like the probability that this x is greater than negative 1, then you just standardize it. And so on the left side, I'm going to subtract the mean and divide by the standard deviation, and usually do it symbolically on the left side, whereas on the right side, I'm going to subtract the actual mean and divide by the standard deviation. And then the thing on the left is a z, it's a standard normal. So this is the probability that z is greater than, and this is negative 1.34. So then if you go to the table, you would, to be above this negative number is quite a lot of area. It's going to be more than 1/2. Yeah, so I think, so you go to the table, and I thought I wrote this down, but I've already closed the table. I think it is 0.9099 from the table. I need to check that, but I think that's what you would get, because it's going to be the same as the probability that z is less than 1.34. Okay, so the last thing I want to say here is that suppose you have x1 through xn IID from some distribution with mean mu and variance sigma squared. Let me be more specific in this example. From a normal distribution with mean mu and variance sigma squared, then if we want to find probabilities for x bar, the sample mean, we can turn it into a standard normal. So we know the sample mean is normally distributed because it's a linear combination of normals. And we know this, the mean of the sample mean is always mu, and the variance is sigma squared over n. So we know it's this very specific normal. So when we standardize an x bar, you're going to see a square root of n pop out. And sometimes people say, why do you sometimes have the square root of n and sometimes don't? And I just want to reassure you that nothing is different, because we can turn it into a standard normal by subtracting its mean and dividing by its standard deviation. So that's always how it goes. It's just that for x bar, the mean is the original mean, and the standard deviation is the square root of that variance. So this guy is normal 0, 1. And with that, we've come to our central limit theorem example. Okay, so this is going to be an example of the central limit theorem. So I'm going to take a sample of size 100, so x1 through x100. These are going to be IID exponential with rate 2. And I want to find the approximate probability. So if you see that in this class, like on an exam, this is the only approximation we have. So if you see, and I think that we will have, so if you see approximate probability, central limit theorem. So the approximate probability that x bar is less than 0.6. I can do this exactly, and I will, and we'll compare the numbers. But you just say that, okay, so you see approximate, and that says ding, 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 central limit theorem. So you need the mean for x bar, which is the mean of the original guys, which is the expected value of any one of these. And that is 1/2 for this exponential rate 2. And then you need the variance for x bar, which is the original variance over n, which is, again, the variance of one of them over n. And the variance of the exponential rate lambda is 1 over lambda squared. So this is 1 over 2 squared. So this is 1/4 over n, which is 100. So this is 1 over 400. Okay, we're ready to go. The probability that x bar is less than 0.6, I'm going to standardize both sides. So on the left, I'm going to subtract its mean and divide by its standard deviation. And on the right, I'm going to do that numerically. So 1/2 over the square root of 1 over 400. Okay, so I did the sigma and the n together in a square root, right? I just did sigma squared over n all in the square root. So then you say, by the central limit theorem, this guy is approximately standard normal. And so we can say this is approximately the probability that z is less than whatever this is. And this, I think, one would be 2, 6. Yeah, I think this is 2. So bad with the actual numbers. Where z is a standard normal random variable. Okay, so you go to the table, you're going down the column to the 2.0, and then across the top, you're grabbing the first column, which is 0.0, and the number you find in there is 0.9772, our first approximation. We can do this one exactly, and let's do it. So the exact answer, and this is going to lead you to someone asking, what is the rate of convergence here? So before saying the exact answer, we're using the fact that the x bar is, in some sense, as things get large, approximately normal. And what is large? So here I had a sample of size 100, and I don't know, I was telling you last time that most textbooks and papers, they all say large is a sample size where n is greater than 30, which I've already told you I hate, because that is, a horrible approximation to infinity. Some of them say 40. Wow. Let's see what we get here. I can't actually give you a rate of convergence in general, because it's going to be really dependent on the underlying distribution. So if I start with something closer to a normal distribution, like a gamma distribution with the right parameters, so it's already kind of Bellish, then I actually can do this exactly and match the answers to these 4 decimal places that I've written down. The exponential being, quite a different shape from the normal is probably going to be a little worse. And again, I can't give you rates of convergence in general. It's going to be underlying distribution dependent. Okay, so let's do this. We know that the sum of exponentials, well, first of all, we've got 100 exponentials. And we know if you add up exponentials, you get a gamma, and the first parameter is the number you've added up, and the second parameter matches the parameter for the exponential. We also saw early on in this class that if x is gamma alpha beta and c is a constant greater than 0, then c times x is gamma alpha beta over c. We showed that as our first example of our G inverse stuff. So going back to the left side, I've got that x bar is 1 over 100, sum as I goes from 1 to 100 of the xi, and this is gamma with first parameter 100, and then the second parameter is going to be 2 over 1 over 100. So this is going to end up being 200. Okay, just stop me if there's any questions. But the probability that x bar is less than 0.6, we could integrate from the bottom of the space, which for the gamma is 0, up to 0.6, this gamma PDF. So 1 over gamma of 100, which is a large number. That's 99 factorial. 200 to the 100, which is a large number. X to the 99, e to the minus 200x dx. I stuck this into Mathematica and it creaked at me a little bit. Didn't take very long, but I like looking at this every year to see how it's improved. And it was just a few seconds, and my computer made a clicking noise. But in Mathematica, I got 0.9721, which we can compare to our approximation of 0.9772. And it's all right. Like I said, if I'd started with something that had more of a bell shape to begin with, like a gamma, then I think we would see a 4 decimal place match here. And again, the rate of convergence, it's really underlying distribution specific. So next up, we're done with the central limit theorem for now, but I want to go back to where we started before the central limit theorem, talking about convergence and distribution. And I have a question for you. So forget the central limit theorem, but just go back to convergence and distribution mode. If xn converges in distribution to x and yn converges in distribution to y, if we look at xn plus yn, back when I was talking about convergence and probability, I wrote down a theorem that kind of looked like this, and then I was like, of course, what is it going to converge to? Of course it's going to be x plus y. But it's actually not true for convergence and distribution. So no, not in general. Which is maybe surprising, but maybe not surprising, because convergence and distribution is so weak, and it's not really saying anything about the random variables. So here is an example of the no. If I let x1, this is like the 3rd time I've used this example, which is nothing's moving. So I let x1 through xn be IID, normal, mu, sigma squared. Nothing is moving in n. And then I let x be normal, mu, sigma squared. Then we clearly have xn converging in distribution to x, because the CDFs for all of the xn's are all the same, and they're the same as the CDF for x. So when you take the limit, nothing's moving. But if we consider like a new sequence of random variables yn defined to be the negative of xn, by symmetry of the normal distribution, it's really easy to show, or at least believe, that this also has a normal distribution. Not true. I need this to be centered at 0. So let me go back and change my normal. I'll use a correction color as 0 and sigma squared. Now when I take the negative, that is again a normal centered at 0 with variance sigma squared. So I've got y1, y2, etc., IID, normal, 0, sigma squared. Okay, so I've got that the YNs converge in distribution to a random variable y, where y is normal with mean 0 and variance sigma squared. But if you add them together, xn plus yn is always 0, and that is not going anywhere. Always not somehow turning into a normal distribution. The reason you have to do problem 5 on the homework is to help us get around this a little bit. So the next thing I want to just state, and unfortunately we really can't prove it, you need measure theory, which is my other course. There's another commercial. And it's called the Continuous Mapping Theorem. And it says that if xn converges in distribution to x, and g is a continuous function, then g of xn converges in distribution to g of x. Again, this requires just way too much stuff to try to go off on an aside. I think it would take us a couple of weeks to build up the stuff we need to prove this, and none of it is really a math stat. The continuous mapping theorem is often written with 3 bullets. So one is convergence and distribution, another is convergence and probability, although we already had that if G is continuous at the end of a theorem. Remember back when we were looking at the triangle inequality that day? We showed that if G is continuous, it does preserve convergence and probability. And then the third bullet you usually see is something called almost sure convergence, which we also don't get to cover because that also requires some measure theory. But that is a strong type of convergence. So how can this help us with the problem we just saw about the sums of the random variables not converging in distribution to the sums of the individual limits? Check this out. This continuous mapping theorem holds even if x is vector valued. So x may be vector valued here, and so suppose we have like the vector xn, yn converging in distribution to xy. So you've seen a joint. I gotta stop making that noise. Okay, so thank you. If we have convergence and distribution jointly, so this is like convergence and distribution of a vector, and yeah, I'm using z, and this has nothing to do with the normal. Then we're talking about convergence and distribution of a vector valued random variable. And so this means the limit as n goes to infinity of the joint CDF is equal to the joint CDF of those guys. If we have that, then we can apply the continuous mapping theorem, and we can say that the sum of these random variables converges in distribution to the sum of the limits. So then xn plus yn is going to converge in distribution to x plus y using g of xy equaling x plus y and the continuous mapping theorem. It is easy to show that we have this kind of joint probability moving to this joint probability if xn and yn are independent. For sure, we can show that pretty quickly, but they don't have to be independent and aren't for the interesting examples. Okay, so this relates to problem 5 on the homework, but I'm not ready to tell you about that yet. And I did give a long hint on the second page of the homework, and I regret now how fast I was doing it. I cut and pasted it from an old document I wrote. I really feel like I should have had X's and Y's in there, but I was writing things like this with Z1s and Z2s. I just think it looks funny in the context of the problem. So if you want to replace every little lowercase z1 with x and every lowercase z2 with y, go ahead or don't.
Can you explain how this relates to the sort of the counterexample we just showed above for?
Yeah. So actually, I can't do this particular example because I can't write down the CDF or the normal distributions in closed form.
But so it seems like what we just said was
we need them. Oh, sorry. Go ahead.
Well, I mean, it seems like in that previous example, G was. I mean, all we need is G continuous, and X.
Yeah, we actually need this for the previous example to go to this. And I had this marginally going to the CDF for the normal and this marginally going for the CDF for the normal. But in that example, they won't, because of how it was constructed, they won't jointly go to that, except that can't really show that very easily because I can't write down that CDF.
I think you could write down the CDF for their sum, though, not as a joint.
Yeah. But the sum is always 0, so.
Right, it's kind of trivial, I suppose.
Yeah, so Cooper, the reason this didn't work in that example, although you're not seeing it from this, is they didn't move jointly to some joint distribution. Well, they do, but not the distribution you're thinking.
And if we were going to apply this, we'd need to find the joint distribution.
Yeah.
Okay. Yeah. So that makes sense.
But if they are independent, then this joint distribution, if you had independence, which I'm not saying you have here, then this would be the two guys, which would go to the two limiting distributions, and all would be well. My example, they definitely weren't independent.
Yeah. Okay.
Other questions? Okay. So the last thing from this, not the last thing, the second to last thing from convergence and distribution is a very famous theorem known as Slutsky's theorem. And this, I always end up putting a Z in there, it's an S. Slutsky's theorem. This is a theorem where you can combine some limiting results. You can combine some results for convergence in distribution and convergence in probability. So, this made me want to say something. I'll say that later. Slutsky's theorem says that if you have a sequence of random variables xn converging in distribution to a random variable x, and if you have a sequence of random variables yn converging in probability to a constant a, where a is a constant, then you can combine these guys in certain ways and get kind of what you would think. So if you look at xn plus yn, this is going to converge to x plus a, and it's going to do it in the weaker sense, which is convergence in distribution. Now you're actually proving this in problem 5 on the homework, because in problem 5 on the homework, I gave you a setup like this. I think instead of A, I used B. And I'm having you show that these two things together imply that as a vector, this is going in distribution to this. This is problem 5 on the homework. So if you show that, then this result here in Slutsky's theorem is just the continuous mapping theorem. Does that make sense? And this looks long, but I did do more than half of the problem. I gave you a head start and gave you some hints. And then to finish writing down Slutsky's theorem, we also know that xn times yn converges in distribution to a times x. Again, it's always the weaker form of convergence that dominates, but if this capital X is a constant, then we can say convergence in distribution to all the right-hand sides will be constant, and that does imply convergence in probability. And the last one here is the ratio. Xn over Yn is going to converge in distribution to X over A as long as A is not 0. So again, the thing I just said is that if this X is constant, then all of these are going to a constant, in which case convergence in distribution is equivalent to convergence in probability. So you have convergence in probability for all of these. And proving all of these are all continuous mapping theorem. You're just redefining these G's, right? You've got like a G of xy is x plus y, or x times y, or x over y. And I guess I didn't state the continuous mapping theorem completely accurately. I said that G had to be continuous, but it actually only has to be continuous because there's a problem with this ratio. If it has discontinuity, that has to be on a set of points whose probability is 0 of occurring. I mean, we say in measure theory, a set with probability measure 0. So once you prove problem 5, we have proved Slutsky's theorem. Questions? Okay, and this is going to help you do problem 4. Bring up the homework. So homework 5, number 4. It says that you have a sequence of random variables, x1, x2 on up, such that the square root of n, xn minus mu is converging in distribution to a normal 0, 1. Sorry, I went way up in the corner. This is actually shorthand for, it should really be written as the square root of n, xn minus mu converges in distribution to x, where x is normal 0, 1. And the reason I bothered to write it like that is because in this problem, you want to show that xn itself, like if you have this, then you have that xn itself converges in probability to mu. So we want to show that xn converges in probability to mu. And so check this out. I can write xn in terms of this thing. Like I know something about the convergence of this. So maybe I could write it as 1 over the square root of n, square root of n, xn minus mu, and that's almost xn, but then I have to add on a mu. This problem is done because this guy, by assumption here, converges in distribution to the normal 0, 1, random variable x. The constants out here converge in probability, you know, as boring random variables, converge to 0 as n goes to infinity. So by Slutsky's theorem, this stuff together will go in distribution to 0 times x, which is 0. And you have to add on that mu, which is like nothing, to get the desired result. So Slutsky's theorem is quite useful. And we just did problem 4 on homework 5. Okay, the last thing I have for you is something that's not in the notes, which reminds me that today I posted a new page where I am posting handouts of things that are not in the notes. So I posted a thing on order statistics today. You don't have to know that stuff. I just wanted to fill out some of the information that I didn't give. So on one of our homeworks, we looked at some heuristic explanations about why the joint PDF for the kth order statistic and the ith order statistic looks like something. And so that handout gives you the actual proof of those things, but we don't need them for this course. We rarely use anything but the min and max. So you can read that or not read that. But this next thing is not in the notes because it's something that's never done down in 4520, 5520, and I'm going to put an addendum on that same page this weekend, and it's called the delta method. The delta method is to show convergence in distribution of something in a very specific setting. So I'm going to let xn, I'm supposed to be a pro at these brackets. I'm going to let xn be a sequence of random variables such that the square root of n, xn minus theta, it's probably going to be the mean mu of the distribution, but it doesn't have to be. If you have this going in distribution to a normal with mean 0 and some variance sigma squared, where sigma squared is finite. And by Slutsky's theorem, we can actually move the sigma. We can put the sigma on the left side in a way that's going to make this go to a normal 0, 1. But the point of the delta method is if we let g be a function from r to r, the reals, be such that it is continuously differentiable, at least in a neighborhood of theta. Theta is a fixed, and for us, usually unknown parameter. So continuously differentiable in a neighborhood of theta. And we also need that g prime of theta is not 0. So if you have all this stuff, then here is the punchline. The square root of n times g of xn minus g of theta is going to converge in distribution to a normal with mean 0 and variance sigma squared times the derivative of g evaluated at theta squared. This is going to be easy to prove, but I don't know if I can even start it. I think I'll use this time to show you an example of this, and we'll prove it next time. So, as an example, suppose I have x1 through xn, IID from any distribution, so I'm not putting the n here, sigma squared and mu for the variance and the mean. We know from the central limit theorem that the square root of n x bar minus mu over sigma is converging in distribution to a normal 0, 1. Let me give this a name, z, where z is normal 0, 1. And so if we multiply both sides by sigma, Slutsky's theorem tells us that the square root of n times x bar minus mu is converging, and I mean to put distribution over that arrow, to sigma times x. And the distribution of this is another normal. the distribution is normal because I'm taking a normal and multiplying by a constant. And the expected value of sigma x, the sigma would come out and you still get a mean of 0, but if you take the variance, the sigma comes out squared. And so this is a normal 0 sigma squared. I didn't use the delta method yet, but what I want to use the delta method on is, so by the delta method, we can say, for example, that the square root of n times x bar squared minus mu squared, so I just picked a simple little function g of x being x squared, is going to go in distribution to a normal with mean 0, variance sigma squared, and then in here I'm going to put, so I have g of x equals x squared, and in here I'm putting g prime of mu, or theta in general, squared, and that's going to be 2 mu all squared. So I am out of time, but if I move this variance back over, we can conclude that x bar squared is asymptotically normal with this mean and this variance. And I will clarify that next time, and we will prove the delta method. So have an awesome weekend. Thank you.